Hi everyone, welcome to the final lecture of this course on microsensors and nanosensors. We are actually discussing module 12 where we were discussing sensors for healthcare, and this final lecture of this module I have preserved for just reviewing the complete course. Okay, so if you remember, this course was divided into 12 different weeks, and each week was actually dedicated to a module. Okay, so in the first module or in the week 1, we have talked about different classification of sensors after we introduces the sensor. Okay, so a sensor was if you remember, in terms of electrical engineering, we have discussed everything. Okay, so sensor without as a translator which convert some non-electrical value to certain electrical value. And here the word electrical refers to a signal that can be channeled, that can be amplified, or they can be modified by some electronic devices like a transistor or even with the amplifier. Okay, so then we talked about 3 different terms, that is sensor, transducer and actuator, and we have given considerable amount of time to understand the difference between them. Okay, so transducer was a device which converts any useful form of energy to another form of energy. Okay, so sensor is a device which convert any useful energy to the specifically to electrical energy, while actuator was a device which convert the electrical energy to another form of energy like heat energy or some mechanical energy. Okay, then after this introduction, we talked about different ways to classify the sensors, and 3 different ways to classify these sensors were based on the transducer function, based on the energy that they require, and based on the selected reference. So based on the transducer function, we have seen 2 different kind of sensors, that is direct sensor and a complex sensor, and we have understood them with some example. Based on energy, we have seen 2 different sensor categories, that are passive sensors and active sensors, and during the course also most of the time we were identifying these sensors, that if they fall under the class of passive sensor or under the class of active sensor. Okay, and then based on the selected reference, we have classified these sensors into 2 different types, that is absolute sensor and relative sensor. Okay, then we have also seen the classification based on the properties. Okay, and based on the properties also we have seen various categories, like based on stimulus, based on means of the detection, based on the sensing material, as well as based on the conversion phenomena. Okay, then we have in this module talked about fabrication steps to get a microsensor, and in that we talked about wafer selection and cleaning first. Okay, then we have briefly seen a photolithography technique. Photolithography you can also refer to some device technology book or VLSI technology book, where you can find them in more detail. We are just covering it under one module, so we have not discussed in detail, but then I have given you a brief idea about lithography. Okay, then we talked about deposition and removal. Removal were including 2 different type of etching, like wet etching and dry etching. And then we talked about oxidation. Oxidation like both in terms of deposited oxide as well as thermally grown oxide. Okay. We talked about doping also in module 1, where we talked about 2 different doping techniques, including diffusion and ion implantation. Okay, and all these sensors will require metallization for making contact as well as for interconnect purposes. So we have seen metallization, and little bit I talked about die preparation, packaging, and their electrical and mechanical testing. Okay. And all of these were elaborated briefly. Okay, so for that we have seen, for example, for deposition, we have seen deposition by 2 different ways. One was chemical vapor deposition and another was physical vapor deposition. We have seen that chemical vapor deposition itself can be of various type depending on the pressure utilized in the chamber. You have atmospheric pressure based CVD systems, and you have low pressure based CVD system. Depending on what kind of wall you are using. You have hot wall tube and cold wall tube kind of atmospheric CVD systems with depending on the way of bringing vapor and vapor, I mean their reactions, you have continuous motion and batch type of atmospheric pressure CVD systems. Okay. Similarly, we have seen PECVD, vertical flow, hot wall batch, cold wall single wafer, different kind of CVDs, and another kind of CVD that we mentioned was MOCVD. Okay. In PVD, we have seen different deposition technique, including the evaporative techniques and sputtering based devices. In evaporative, we have seen thermal evaporation based, electron gun based, inductive, resistive and arc based evaporation, and in sputtering we have started with the triode, and then we talked about ion beam sputtering, magnetron, diode, RF and plasma, pulse plasma kind of sputtering system. Okay. Then we jumped into week 2 or module 2, where we talked about sensor characteristic. Okay. So the sensor characteristics were of two different type. One was static characteristic of sensors, and then we have also seen the dynamic characteristics of sensor with a focus on static characteristic of sensors. Okay. In the static characteristic of sensors, we have talked about number of characteristic, and we have utilized them till our 12th module. Okay. So we have talked about transfer function, which has also helped us in calibration. Okay. So transfer function, then we have also seen the sensitivity, the calibration itself. Okay. Span, which was also called as full scale input. Okay. We also talked about full scale output, accuracy, hysteresis and hysteresis error. Okay. Non-linearity, saturation, repeatability, deadband, resolution, output impedance and input impedance of the sensors, output format of the signals, okay, excitation, reliability and uncertainty. Okay. We have seen more or less these characteristics during our discussion of module 2. Okay. The dynamic characteristic of these sensors were of 4 different type, including the speed of response, measuring lag, fidelity and the dynamic error. We have seen these dynamic characteristic of the sensor in little detail. Okay. Then we also talked about noise, which is nothing but a spurious current or voltage, which is irrelevant to the signal current or voltage in a electrical circuit, and we have seen different type of noise, and based on the signal to noise ratio, which is the ratio of signal power to noise power, we have seen different ways how we can maximize signal to noise ratio or minimize the noise in a device, mostly through the interface circuits. Okay. So in module 4 actually we have discussed the interface circuits in more detail. Okay. Different type of errors which arises from different sources we have also discussed in this second module. There were 3 different type of errors. One was gross error, systematic errors and random errors. Okay. Systematic errors we have seen in detail with 3 different categories of systematic error, which is instrumental error, environmental errors and observational errors. We have talked about them in detail. Okay. Then in the third module we have mostly talked about principle of sensing. So we have seen that various class of actually physical effects exist, which can be converted to electrical signal by different means, including capacitive ways, inductive, resistive, piezoelectric effects, pyroelectric effects and some more effects we have seen like Hall effect, but that we have specifically seen for particular device, not in the principle of sensing, because that were very specific to a certain device. Okay. But this is not the exhaustive list. We have discussed some other kind of principles also. Okay. So mostly these techniques we have seen that can be utilized for direct sensing, and the fourth module was on interface circuit. So the idea of interfacing circuit was to give the output from the sensor or convert the output from the sensor to a signal which can be fed to a load device. Okay. And then it can be fed to a system so that the end user can interpret the data. Okay. So this kind of conditioning is mostly done using this interface circuit. Okay, so the requirements of this sensors interface circuit were enormous. We have seen that a number of things are required, including amplifiers, excitation circuits, current to voltage or voltage to current regulators, then charge to voltage converters, ADCs and DACs, data transmission and noise suppression strategies can also be made based on interface circuits. Okay. Then we also talked about filters. Filters are designed to pass the signal of wanted frequency and to reject the signal of unwanted frequency which is coming from a sensor. Okay. These signals which you want to remove can also include noise along with the harmonics which is not wanted by the end user. Okay, so two different type of filters we have seen, active and passive, and then further we have divided them under different heads. Okay, we have also talked about current generators and their main characteristics were the output impedance which is actually high and the voltage compliances associated with them. Okay. Then we have discussed the fifth module, which were having two different components. One was a physical sensor, which was the humidity sensor, and the second was a chemical sensor, which mostly include the gas sensors or toxic element sensors. Okay, so the fifth module was mostly dedicated to humidity and chemical sensors. So we started this module with a discussion on water vapor content in air and how to define the humidity. We have seen that there are three different ways to define humidity. One was absolute humidity, then specific humidity, but for us the relative humidity was more relevant. So relative humidity was defined as the current, it is the current absolute humidity, which is the ratio of humidity that exists right now to that of maximum that can exist at that particular temperature. Okay, we have also seen this definition in terms of partial pressure, but this was the crude definition that we have utilized, and throughout this course we have only utilized this RS term. We have not talked about absolute humidity or specific humidity. We have seen mostly 6 different devices to detect this humidity, including optical devices, gravimetric devices, piezoresistive devices, simple resistive devices also, magnetoelastic devices, and the capacitive devices. And we talked that most of the sensors, in fact more than 85% of sensors, humidity sensors that are there in the market are based on capacitive principle. Okay. In the chemical sensor, we have also seen that there are different ways or different transduction techniques to detect these chemicals, including chemiresistive devices, where a simple change in resistance is measured with respect to the molecules which we want to detect. So you have a surface of a receptor, you have a transducer, and these molecules interact with the receptor, and along accordingly the receptor changes its resistance. Okay. Then we have capacitive devices, where this change is not in terms of resistance but in terms of capacitance. Okay. Then we have seen optical sensor, which is based on number of optical phenomena, including reflection, absorption, interferometry based on fluorescence, change in refractive index, or even with the change in the optical path length. Okay. Then we have also seen field effect transistor based chemical sensors in detail, where we have seen that there is a change in the channel current and change in the work function, which is basically is measured. Okay. The piezoelectric devices were mostly based on change in mass, and we have also talked about electrochemical sensor in other module, where we mostly talk about glucose sensors. Okay. Particularly in this 12th module. Okay. So we have also seen that these gas sensors, along with the pollution monitoring and other application, can also be used for disease diagnosis. And for disease diagnosis, we have seen that they mostly capture different biomarkers. Like for example, for interstitial diseases, you have hydrogen and methane as a biomarker. For lung cancers, you have aldehyde, toluene, and for halitosis, you have H2S as a biomarkers. Okay. For asthma, you have some gases like ethane and pentane. Similarly, for chronic kidney diseases, ammonia and isoprene are different biomarkers, and for diabetes, we have acetone and isoprene as breath biomarkers. Okay, and the different techniques again are based on electrical, optical, in the change of mass, in the change of capacitance, etc. The next module, the sixth module, was of another physical sensor where we talked about temperature mostly. The temperature sensors we have seen were mostly categorized under two heads. One was contact temperature sensors and another was the non-contact based temperature sensor. In non-contact, we have mostly seen the optical IR sensors and that too dominated with the passive IR devices, and in the contact sensors we have seen a number of devices including the RTD, which is the resistance temperature detectors, then thermistors and the thermocouples. Then there was one more temperature sensor, which was the thermopile, which is nothing but mostly a series combination of these thermocouples. Okay. Then we talked about in detail about all these devices, including say thermistors, which are again of various type like NTC, PTC, that kind of devices. So we have seen their characteristic in detail. Okay. We have also seen a semiconductor PN junction based temperature sensor, where we discussed that for a diode or for a bipolar transistor, you can use the PN junction in it as a temperature sensor. Okay. So when a constant current generator is applied to say a forward bias junction, the resulting voltage actually indicate the measure of the junction temperature, and exactly we have utilized to develop these semiconductor PN junction based devices. Okay. The seventh module was on force sensors. The method of sensing force we have seen can be based on the following way. It can be by balancing the unknown force against the gravitational force of a standard mass, and by measuring the acceleration of a known mass to which the force is applied. Exactly same thing we have also talked in the module where we talked about the accelerometers, where we have, if you remember, we had a proof mass, and this was balanced against some external force, and it was calculated by going reverse by mass into acceleration to say, if it is spring based devices, then mass into acceleration was equated to say spring constant into the displacement. Okay. So we have seen a number of arrangements, and all these modules are actually interconnected. So mostly this force, pressure and the accelerometers modules were connected to each other. So if you understand one module, it will also help you in understanding the other module. Okay. So the two methods that we talked about for force detection was by balancing the unknown force against the gravitational force of a standard mass, or by measuring the acceleration of a known mass to which the force is applied. Okay. Other methods were by balancing the force against electromagnetically developed force, or by converting the force to a fluid pressure and measuring that pressure and utilizing this area to calculate the force. Okay. Or by measuring the strain in an elastic membrane due to some unknown force. Okay. So the principles of these sensors were utilized for fabrication of different sensor using different transduction techniques. Okay. So you have strain gauge based force sensor, then we talked about piezoresistive force sensors, we also talked about piezomagnetic and capacitive force sensors. Okay. Then another class of force sensors were the optical force sensors and vision based force sensor, which is a kind of image processing based devices, and within a certain polymers we have seen that there is a electroactive force sensors can be made, which is very specific to the electroactive polymers. Okay. In the next module, in the 8th module, basically we have talked about two different kind of sensors. One was the tactile sensors and another was the pressure sensors. Okay. Tactile sensors, if you remember, are the devices that mimic the sense of touch in human. Okay. So they detect some physical interaction in the form of either force or pressure, vibration, or even in the form of texture. Okay. Further, these tactile sensors convert the mechanical stimuli into electrical signals, because these are sensors. So the mechanical stimuli has to be converted to some electrical form of signal. Okay, these sensors were specific type of force or pressure sensors with very thin layers of material or the receptors. Okay, they can be created or can be fabricated by creating situations where force or pressure can be built up between two objects that are close to each other. Say one of the example was like this. So you have two piezo resistors in place, and then you had this diaphragm kind of thing, and once you pinch it, if this material touches it, means there is a kind of short circuit or voltage is 0, and this is red, and accordingly the force is calculated, or at least you can say that if it is touched or not touched. That is the exact work of tactile sensor. It doesn't care about the amount of force or amount of pressure. Of course, there are certain thresholds in the device, but beyond that threshold it doesn't care, and it gives you the sense of touch or not touch. Okay, so different type of tactile sensors were included: the touch sensors, the spatial sensors, and the slip sensors based devices. Okay, they were using different transduction techniques like resistive, then optical based devices, capacitive, tunnel effect, ultrasound, or magnetic, as well as the piezoelectric. Okay. Then in the same module, there was another section of pressure sensor where we talked about the fabrication and characteristics of pressure sensor. The working principle of pressure sensors was based on converting the impact of pressure applied to a sensitive element in terms of force with a specific defined surface area. Okay, there were different sensing elements with a known area for the devices, like they were based on diaphragm, based on plate, and we have also talked about pressure sensors based on membranes. Okay, so these membranes or plates or diaphragm deform under the pressure, and for a known area the pressure can be calculated. Okay, the transduction mechanism that we have seen were the piezoresistive, capacitive, piezoelectric, and optical. Okay. We have seen several fabrication strategies for developing these pressure sensors, including the bulk micromachining, surface micromachining, soft lithography, printing techniques, additive manufacturing, and hybrid techniques like combination of CMOS and MEMS technologies. Okay. In the 9th module, we talked about occupancy and motion sensors. And if you remember, we have also covered these occupancy and motion sensors in the 11th module, where we talked about sensors for smart building, and that was necessary because the occupancy and motion sensors are utilized in smart buildings at most. Okay, so they are the typical example, or the smart building was a particular application of this occupancy and motion sensors. Nevertheless, we have talked about other kind of occupancy and motion sensors which we could not cover in this 9th module. Okay, so that we have covered in the 11th module. Okay, so when we started this 9th module, we have segregated the motion sensors and occupancy sensors clearly. We have seen that the motion sensors detect when something is moved, something has moved. Okay, while occupancy sensor is when something is there or not. Okay, if even it is not moving, it doesn't care, it just detect it. Okay, there were different occupancy and motion sensors, and the principles were based on ultrasonic, microwave, capacitive, triboelectric, and optoelectronic. And in this module, actually we talked about the Doppler's effect, and we have also seen that how the microwave based devices also simplifies to work on this Doppler effect. Okay, we have also discussed about the IR motion detectors. There were two type of IR motion detectors, that are passive and active devices. The passive infrared motion detectors or PIR motion detectors is very popular, because of their application in security and energy management system. So we have seen the PIR sensors in some more detail. Okay, the applications of this occupancy and motion sensors were not limited to the smart building, but it was also equally useful for security, surveillance application, energy management, personal safety, point of sale advertisement, and for the interactive toys. Okay. The 10th module, which was essentially our last module in discussion of these sensors, because 11th and 12th module we have dedicatedly seen two different applications for societal benefits. Okay, that was for smart building and for healthcare. Okay, so 10th module we have mostly covered the displacement sensors and accelerometers. We know that all these things, position, velocity and accelerations, are interrelated, but then also we have seen the conditions where if you obtain the position, even you know all the parameter, deriving the acceleration is very difficult, or it can be in practical sense very noisy. Okay, so to learn about these devices individually are better. Okay, so for displacement sensors we have seen number of devices based on different transduction techniques like potentiometric devices, capacitive devices, eddy current based devices, magnetostrictive devices, optical sensors, then ultrasonic displacement sensors, Hall effect devices, and then linear variable differential transformer and rotary variable differential transformer based displacement sensors. Okay, for accelerometers we have seen their characteristics separately, although we have discussed different characteristics of the devices in module 1, then also we have segregated the characteristics of accelerometer, because here the moving mass is associated, and depending on the frequency range and other things, these criteria changes. So 4 different characteristics that we have seen were the operating range, frequency range, linearity, sensitivity, cross axis sensitivity. Okay, we have talked about number of accelerometers which can be fabricated by MEMS and other technologies, and in that we have seen the capacitive devices, piezoelectric and piezoresistive devices, optical devices, and one more category of accelerometer we have seen, that was thermal accelerometers, where the proof mass was not a physical inertial mass that were present in all the cases. Okay, here the proof mass was the gas which was filled inside a MEMS cavity. Okay, so the gas itself was being utilized as a proof mass. So this segregate this thermal accelerometer from other kind of accelerometers. Okay. Then week 11 and week 12, as I have mentioned, that they were mostly from the application point of view. Okay, so the sensors that are required in smart building were like for occupancy monitoring, for motion monitoring. So you have occupancy sensors, motion sensors. Along with that, you have air velocity sensors, pressure mats, sound sensors, and number of gas sensors, including the volatile organic compound detectors. Okay, we also have seen that you require a lot of photo sensors, ambient temperature sensors, then specific meters for current detection, voltage detection, and power detection. For the water supply, you have water flow sensors. Okay, humidity sensors and acoustic sensors. Okay, so occupancy sensors, for example, we have seen various type of occupancy sensors like passive infrared, ultrasonic, microwave based occupancy sensors. But along with this, we have seen more categories like image based or TOF based, or 3D cameras sometime can also be utilized for monitoring the occupancy. Okay, then for monitoring of all these say temperature and humidity, air velocity, photometric sensors, we have seen number of devices, 2 specific devices which were very specific to building environment monitoring were the particulate matter sensors and the smoke sensors, and we have talked about them in detail. Okay. And then in the last module that we are still discussing, we talked about different sensors for healthcare application, including the biophysical sensor, biochemical sensor, image sensor, motion and activity sensors, and environmental sensors. we, out of all these things, we have finalized 4 different sensors based on the principles of which you can actually derive other sensors, like 4 different categories of sensors for healthcare that we talked about were the glucose sensors, the ECG devices, the pulse oximeters, and MRI. Okay, so glucose sensors we have seen based on various transduction techniques like electrochemical, optical, thermal, piezoelectric, and then MAE, the microneedle based devices. Okay, and the ECG itself were particularly the electrodes were of different type. We have seen that 12 different nodes has to be fixed. Okay, so depending on what electrode you are utilizing, your sensitivity and other characteristic will vary. We have seen that conventional wet AgAgCl electrode can be utilized with certain gel being applied. Okay, then dry metal electrodes, microneedle array electrodes, textile or fabric based electrodes, nanomaterial coated electrodes, and then for the stretchable and conductive polymers like tattoo based electrodes are also possible. Okay. We also discussed the MRI based devices or MRI. MRI we have talked like it's a medical imaging technique that employ powerful magnets, radio frequency pulses, and coils to create detailed image of the internal organs and tissues. Okay, and we have seen that this particular imaging technique is based on NMR and it doesn't require any ionization ions, okay, or ionized particles. Okay, then we have talked about the pulse oximeters, which were the small tiny device, non-invasive device that can measure the oxygen saturation in the blood. Okay, they can monitor the percentage of oxygen bound hemoglobin, the SpO2, and can be simply clipped in our finger. Okay, and these devices were utilizing 2 different wavelengths. One was red and another was the infrared. Okay, and they were based on the principle of spectrophotometry. Okay, so with this discussion of 12 different modules, what we have gained. Okay, first of all, we have now a comprehensive understanding of this course. So throughout the course, we have gained a thorough understanding of the principles, fabrication techniques, and operational mechanism of different microsensors and nanosensors. Okay. Now, if you see this course, this has been designed with the approach of interdisciplinary. Okay, so interdisciplinary is important, particularly for this kind of courses. Okay, so microsensors and nanosensors integrate. If you see the concept of physics, chemistry, biology, electronics, and material science, therefore you can say that this course is truly example of interdisciplinary innovation. Okay. Then the technological advancement that we have discussed is based on the nanotechnology. So all the devices that we have built is possible because of the advancement in the MEMS, CMOS, and other technologies. Okay, so the rapid development in this micro and nano area has enabled the creation of these sensors with improved sensitivity, selectivity, and other characteristics. Okay, and therefore in situ detection of various phenomena is nowadays possible. Okay, so we have seen various technological advancements in all the sensors. Okay, then we have also seen a wide range of application. So we have explored 2 different applications, including the healthcare and smart building. However, these were just 2 examples. These sensors can be extended to environmental monitoring, industrial automation, for defense, and for wearable consumable electronics. Wherever I managed to show the example, I have already shown it, but there were many places because of the time constraint I could not discuss these applications in more detail. Okay, then for the future perspective, I can say that the area of microsensors and nanosensors is dynamic and rapidly evolving, with trends towards further miniaturization of these devices, integration with wireless networks, and intelligent data analytics. Okay, then ongoing research and interdisciplinary collaboration will continue to drive these novel sensor solutions for emerging challenges, particularly for the application of security and for healthcare. Okay, so With this, I really appreciate the help that I have received from my TAs, Arindam and Supriya. I am really thankful to the entire CET team at IIT Guwahati who helped me to realize this course, and that's how I am able to present this course in front of you. And I am really thankful to you, the students who has patiently gone through all the lectures, and I am sure that the course has provided you at least a level of confidence in this area of microsensors and nanosensors. Thank you.